My name is Daren. I'm a software engineer at Amazon Web Services. It's great to see everyone here today. Today I'm excited to be talking to you about real-time generative AI with Apache Flink. So my talk today can be broken down into 4 main sections. The first section is just talking to you about the use case. So for today, we are going to focus on a specific use case around real-time football commentary generation with AI and Flink. Next, we'll talk about what are some of the challenges that you might face when you try to implement a use case like this, and how can we solve these challenges with Flink. For the third section, we are going to walk through a demo together just to see how it works. And lastly, we'll talk through some future big ideas. What could the future of live sports commentary look like with AI and Flink? Next slide, please. Right, so the use case today is live sports commentary generation with AI. What it means is, if you try to think of this in terms of input and output, then the input here is just a live stream of video or the images broken down frame by frame as the input. And the output that we want from this is speech that is generated that talks about the sports commentary in real time. For example, if the input shows that the team has scored a goal, then what we want in the output is a speech, a commentary that says the team has scored a goal. Simple as that. So let's look at how we can do this with a naive approach. Next slide, please. So with a naive approach, LLM are actually getting better these days. And do you know that there's actually LLM models out there that can take a speech, that can take a live stream of videos as input. So we can use the LLM model to just take the live stream of video as input and then just give it an instruction to generate the commentaries for us. Once the commentary is generated in text, we can then pass it through a text-to-speech or TTS client to generate the speech or the audio for us. So this is a naive approach that works quite well. However, it does come with some challenges. So let's look at the next slide. So I've kind of summarized it into 6 challenges that you might face if you do it with a naive approach. The first one is on latency. So as mentioned, LLMs have pretty high latency, especially around token generation. So this is a challenge that we'll need to resolve. The second is on scalability. What if we want to generate commentaries not just for the current game, but for other ongoing games, or even for the whole season? How can we do it in a scalable way such that we don't get throttled, or we don't face any sort of limit, for example, context window, size limit? The third one is hallucination. As you can imagine, in such a highly dynamic use case or environment like real-time sports generation, you really need real-time data in order to make the best commentary. So if the LLM does not have access to real-time data, you can imagine it can be quite easy for it to hallucinate and produce commentaries that are not accurate. The fourth challenge is with enrichment or connectivity or to a sync. So the LLM has generated the commentary. What's next? We probably want to enrich this commentary to make it even better, or we want to just connect it to another data store or to a sync. So how can we do that? Out of the box, LLM does not have a good way to do that. So we need to work around this as well. The fifth challenge is around fault tolerance. What if your LLM server or client suddenly fails, perhaps just due to a transient network disruption? How can we ensure that once it recovers, it can begin producing commentary from where it left off? So to do this, it probably needs to be able to store some states so that it can recover from failure easily. The sixth challenge is around late events. What if in your live stream there's out of order or late events? How can you handle that? In our case, if we think about real-time sports commentary, because we always want to produce the latest commentary, so we probably just want to drop any late events, for example. So how can we handle that? Of course, we could just give the LLM additional instructions so that it can understand how to handle these late or out of order events. But again, that's giving the LLM more responsibility and overhead to do so. So in summary, there are 6 challenges that I see with the naive approach. And as you can imagine, Challenges 3 to 6 can actually be solved with Flink. These are things that Flink are quite good at in enrichment, in fault tolerance, and as well as handling of late events. And if we can provide it real-time data, we can solve the hallucination problem as well. So let's take a look at how we can do this. So here, in the next slide, I'm proposing a better approach that's built on top of naive approach with Flink. So in the next slide, so how this works is, before the game begins, we have a Flink job that uses the async function to send an initial prompt to the LLM to just give it context and to set the scene, to give it the instruction so that it knows what to do next. So in this initial prompt, what we could tell it is we can do a role prompting here, giving it a role. So we can tell the LLM that you are a football commentator, so that it knows its role. Next, we can give it context. Who are the teams? Who are the players that are playing? And what's the field dimension like? And so on. And next, we can give it an instruction so that it knows what to do next. So we can tell it, for example, over the next few prompts, I will give you event updates. So based on this new event and keeping track of the past events, make an exciting comment for me. And lastly, we can also do a few shots learning here. What this means is we just give the LLM some example input and some expected response in the format of JSON. So in this case, I'm telling it that the input event is going to be in the form of JSON, and it's going to contain the player locations and the ball locations in X and Y coordinates. We also explain to the LLM what this example input means. So we tell it that we know that the ball is at this location, which is currently with Alice at this location, and she is very close to the goal, which is at that location. So we just kind of give it some explanation so that it helps with the thinking. And lastly, we tell it to return the output in the JSON that we want. So this kind of how we help it to produce data in a structured format. So this is the initial prompt. It's only done once per game to just set the scene. Okay. Now, in the next slide, we are going to see what happens when the game now finally begins. So when the game begins, the live stream of images are going to come in through the input, and we would first want to convert this input into a structured format, into the JSON format that we want to prompt the LLM with. And in order to do this conversion, we could use a computer vision algorithm called You Only Look Once, or YOLO in short. What this does is it is running on is trained on a convolutional neural network, and what it does is it performs image classification. So you give it an image, and it can classify the players that are in the image, and it can then construct this JSON with the players' locations and the ball location. So once we have this data in a structured format, in this JSON format, we can then write it or ingest it into a Kafka topic. Once it is in the Kafka topic, the Flink job can then retrieve the event and then starts prompting the LLM for the actual comment to be generated. Once the comment is retrieved from the LLM, it can then persist it in state. This is to help with fault tolerance. And it can then send it to a text-to-speech or TTS client to generate the actual speech. And finally, with the speech and the video from the input, it can then stitch it together, stitch the video and the speech together, and then push it to a sync or to a content delivery network ready for users' consumption. And of course, we talk about out of order or late events handling. That can be done in the Flink job as well. In my case, I keep it simple, so just drop if you see any late events, and we only want to produce commentaries on the latest events. So through this example, you can see how we have already solved 4 of the challenges. However, there are still some challenges remain that are not addressed yet. So let's take a look what are those remaining challenges in the next slide. So the challenges are latency. We haven't really solved that yet. LLMs have very high latency in token generation, and we still need to work around that. The second one is on scalability or rate limits. LLM calls are very expensive, and we can get throttled easily. And as you can imagine right now, how the system works is the rate of LLM invocation is directly proportional to the frame per second in the input image. So if your live stream of videos is 60 frames per second, that means you're going to be prompting the LLM 60 times per second. That's a lot. That's not what we want. So we still need to solve that. The third one is around context window. So if you can tell from the previous slide, how it currently works is we are keeping track of the whole list of events that have happened up until now in the context window. We inject it into a prompt, and that's how the LLM gets this real-time data by referring to what has been provided in the prompt, in the context window. So based on this approach, you can imagine that at some point, we are going to run into the context window size limit. So these are the three challenges that we need to solve next. So in the next slide, we are going to dive deeper into each of these challenges and see how we can solve them with Flink. Now, for latency, before I go into analyzing the latency of the system, I just want to let's define the requirements first. What sort of latency should we strive for an application like this or for a use case like this? So for latency, I've kind of set a human commentator as the gold standard that we are comparing against. That means if our AI commentator is not as responsive as a human commentator, it is probably not good enough. So setting human commentator as the gold standard means that we need to match the human response time, which is on average 200 milliseconds. So what that means is for a human commentator, from the moment it sees the game that is happening to processing that image in the brain and then generating the words to be spoken out, this whole response time takes around 200 milliseconds on average. That is pretty fast. That's pretty amazing, I must say. And once the response has been generated, next comes the human speaking speed or talking speed. On average, it's about 3 tokens per second or 2 words per second. So these are the two metrics that we want to look at in terms of requirement. So next, let's break down the current solution that we have and look at what latencies we are currently at. So I've kind of broken it down into 3 components and then analyzing the latency of each component. So starting with the computer vision part, currently with YOLO v5 running on an NVIDIA GPU, processing a full HD image, it can actually do it at 180 frames per second. Or in other words, that translates to a latency of about 6 milliseconds. So that's pretty good. And next, we have the LLM. For the LLM to understand its latency, we need to look at 2 metrics. The first one is time to first token, or TTFT. What this means is it is the time taken from when the LLM received the prompt to when the first token is being generated. The time it takes to generate the first token. Or you can think of it as like the human response time as well, from the time it receives the image to when it produces the first word. So you can think of it as like the human response times as well. The second metric to look at is time per output token, or TPOT. What this means is after the first token has been generated, how long does it take to generate the subsequent token, the next token? Or you can think of it as like the human speaking speed. Once you have started saying the first word, how long does it take to generate, to talk, to speak the second word, the next word? So currently the best 70 billion parameter model LLM running on a GPU can achieve a TTFT of 220 milliseconds and a TPOT of 5 milliseconds, or 200 tokens per second. The third component to look at is the text-to-speech client, or TTS. To understand TTS, we need to look at the first token-to-speech metric, or FTTS. What this means is how long does it take from when the first token is received to when the first byte of speech or audio file is created. So this time is called the first token to speech, or you can think of it as like the human response time as well in a sense. And currently, the best TTS client out there can achieve a FTTS of about 130 milliseconds. Another thing that is not currently on the slide, but I want to talk about is the token rate as well. So that is kind of equivalent to the TPOT, or the speaking speed. How long does it take for the TTS client generate the next token as well. And that is currently at around 50 TPS. So putting all of this together, if we try to compare between this AI and human commentator, let's look at how they fare against each other. If we look at the reaction time, currently the AI commentator is still 75% slower than the human commentator, okay? And I want you to bear in mind as well that I haven't factored in other latency as well. For example, network latency, which is just going to make this even longer. So I would say that currently the AI commentator is not as fast as the human commentator, and this is something that we need to resolve. However, in terms of the talking speed, it's currently limited by the TTS actually. So it's not 200 TPS, but 50 TPS. However, even 50 TPS comparing to a human speaker at 3 TPS, I would say that it has no problem at all in talking or catching up at least to the human talking speed. So I think the key challenge here is around the reaction time. How can we make the LLM react faster? So to do that, let's take a look at the next slide. So here I can think of some optimization or workaround to solve this problem. The first one is we can just optimize the LLM itself. So for the model size, we probably can't pick a model that's too big because that will increase the latency. However, we can't pick a model that's too small either, because if the model is too small, the commentary it generates might not be too meaningful. So from what I can see, 70 billion parameters is kind of the sweet spot. The next thing we can optimize is on the hardware. We can give it the best GPU that we got, and that helps in lowering latency. The third thing that we can fine-tune is the model parameters. So we can limit the max output token, and we can reduce the top case sampling as well. What this means is we just limit the number of the model's choices when it's considering in generating the next token. So when we reduce the top case sampling, it considers less options when generating a next token, and that helps speed things up. We can also enable KV caching. What that means is the output of the attention layer or the KV layer, we just cache the result. And because it's cached, it can be reused, and that helps speed things up as well for the future prompts. And especially KV caching is quite useful in this use case because in the prompt, at the start of the prompt, we are just going to inject the full list of events that has happened so far. So what this means is all these prompts actually share the same prefix in the input. So that's where KV caching can really benefit us here. And lastly, in terms of network latency, we can optimize it by just picking the closest region to host our LLM server. So this is the first option. So the second option, or the second optimization that we can do here is to introduce a fast and slow path, or fast and slow commentators. So what that means is we can have a fast commentator that just use a lightweight LLM to behave like a classifier. And what it is trying to classify here is to select an instant reaction from a list of pre-recorded audio. So for example, wow, amazing, incredible, gold. These are all can be a pre-recorded audio. And how this makes it fast is because we are using a lightweight LLM. And the second thing is we skip the text-to-speech part because all this audio is pre-recorded anyway. So this makes this fast commentator almost instantaneous in giving a reaction. And next, we can have a slow path, a slow commentator that uses the 70 billion model LLM to generate the actual comments and send it to the TTS client to generate the speech. So it's going to be slower, but it's going to produce a more meaningful commentary. So the idea here is that with the fast and slow commentator, hopefully they complement each other in terms of speed and meaningful commentary. The third option here is to extend the live stream delay buffer by maybe a few more seconds. So for those who are familiar with how live stream works, is there's usually a built-in delay or buffer in place. For example, a live stream that you're watching right now probably has at least maybe a few seconds of delay built into it, and it's for good reason. The first reason is to just smoothen out any network jitters to make sure the live stream is smooth. Or even to more practical reasons. For example, in live sports, you add some delays to prevent any form of manipulation in live sports betting. So they are for good reasons. So the third option is to just extend this built-in delay by a bit more. However, to me, this feels more like a workaround, and I'm not really inclined to it. So I'm really focusing more on 1 and 2 to solve the problem of the LLM having a high latency in the first place. So with the option 1 and 2, let's look at how we can implement it in our solution in the next slide. So we now have a slow path and a fast path, a slow commentator and a fast commentator. And on the fast commentator side, we have this lightweight LLM that just, based on the given input event, it just select the instant reaction to be played from the library of pre-recorded reaction audio. And in terms of implementing this lightweight LLM, it can be as simple as just providing a prompt or instruction to tell it that given an event, decide if it's worth making a reaction from a list of available reactions like wow, amazing, and so on. And we ask it to return the response in the format of JSON. And next, so this is how we can optimize the latency. And next, we can take a look at the second challenge, which is around rate limits in the next slide. So again, let's first define the requirements here. What sort of rate limits do we need to deal with to make this feasible? So I've kind of done a back of envelope estimation here. So on average, a commentary is generated at the rate of 15 lines or 15 comments per minute. So the rate of LLM invocation should be around 0.25 TPS on average. However, during a climatic moment, for example, the teams are very close to the goal, are very close to scoring a goal, you would imagine the commentary rate to spike up. Here, I assume it will spike up by at least 3 to 5 times, so up to 1.25 TPS. So these are the requirements that we need to work with: an average case of 0.25 TPS and a burst rate of 1.25 TPS. And I just want to remind everyone, currently the solution we have is still directly proportional to the frame rate in the input video. So we are definitely exceeding the TPS here. That's why we need to optimize this. So if we look at the next slide, I can think of 2 ways to optimize the rate limits here. The first approach is to aggregate or to batch the events. So what we could do here is we can introduce another Flink job to aggregate or batch the events. And how this helps is it reduces the number of LLM invocation. So we group these events together before sending it to the LLM or prompting the LLM. The second optimization that we could do is filtering. So we can add a filter to filter out less meaningful events so that we don't send a prompt to LLM for less meaningful events. So the way we can do this is we could do an anomaly detection. So if the player's position hasn't changed much, then it's probably not too exciting, and we probably don't need to prompt the LLM for a comment. The second way I can think of to do it is to use a lightweight LLM as a classifier. What this means is we give it the event, and based on the event, we ask the LLM to classify whether this is a meaningful event or not, whether we should be making a comment or not. So now let's look at how we can implement both of these approaches into the existing solution that we have. So we add this to the slow path because here we are really more concerned about the rate limits of the LLM that generates the actual comments. So what we could do is before reaching the LLM, we let it first pass through a Flink streaming operator, a windowing function, and to reduce and to aggregate it as well. After the events have been aggregated, we then pass it through the lightweight LLM for filtering. And only if it passes the filter, then it reaches the LLM to generate the comments. So to implement this lightweight LLM, again, it can be implemented as simple as a prompt or an instruction. So here what I tell it is, given the new event and keeping track of the past events, decide and explain if it's worth making a comment, and then return your response as a JSON. Here, I've kind of asked it to provide an explanation or chain of thought on why it thinks it's worth making a comment or not. But in production, if you want to make it even faster, you can even skip the explanation stage as well. And I've also given it some guidelines, some rules to help it to act as guideline for it to decide when it is worth commenting and when it's not. For example, I tell it that if the ball is being passed between players or if the ball is just moving very fast or very close to the goal, it is probably worth making a comment. If there has been no comments for 5 times or 5 events in a row, then that means it's a bit quiet and we ask it to make a comment. If there has been 2 comments in a row or too many comments in a row, we probably want it to cool down or slow down a bit. So we ask it to, maybe it's not worth commenting for a situation like this. So this is how we can implement a filter. And hopefully this helps reduce the rates that we are calling the LLM. Next, let's take a look at the third challenge, context window. So again, let's take a look at the back of envelope estimation to define the requirements of what context window size that we need. So assuming a comment does not exceed the length of 75 words, we can limit the max output tokens to around 100 tokens. And 100 tokens per line multiplied by 15 lines per minute multiplied by 90 minutes, which is the duration of a football match, this gives us 135,000 tokens. So what that means is for a total game, we would require 135,000 tokens. And more is needed if we want to store the context not just for the current game, but for other ongoing games or even for the entire season. So right now, the state-of-the-art LLM models can handle 32,000 tokens with minimal trade-off in latency. However, bear in mind that LLMs models are getting better and better every day. So I would imagine this is going to have significant improvements soon as well. So now that we have defined the requirements, let's look at what are some of the options to optimize this. So in the next slide, here are some optimization that we can consider. The first one, again, is to optimize the LLM itself. We can simply pick a model that supports a large enough context window for our use case. The second and third approach is similar to before, where we try to aggregate, batch, or filter out the events. And the idea here is if we can filter out the events or batch the events, that means we need to only store less events in the context window, and that helps optimize space. The fourth approach is new. We can use RAG or retrieval augmented generation to reduce the context window size that is required. So what this means is we can simply store the older events in a knowledge base, typically implemented using a vector database. Once it is in a vector database, the LLM can then use RAG to retrieve the context of the older events from the vector database and then augment it, inject it into a prompt so that the prompt has these contexts of older events and then generate the commentary for us. So with RAG, what we have done is we have basically moved the storage of these older events from within the context window into a vector database. And that really helps in optimizing the context window size that we need. The fifth option is we can just choose to do nothing here. And what that means is that the oldest event in the list will just simply be evicted from the context memory when we reach the limit. And this is probably acceptable, assuming that the new token doesn't pay much attention to the older events when it's generating the new token anyway. So if that is the case, if that assumption holds, then we can probably just choose to do nothing. So these are 5 options that is considered. Here, let's dive deeper into how we can implement RAG to solve this problem. So in this slide, so what you can see is the Flink job, when it receives the event, it parallelly sends a prompt to the fast path and the slow path, and in addition to that, it also parallelly embeds and stores the event in state and to the knowledge base in real time. So the knowledge base here is being updated in real time, and then the LLM can just use RAG to retrieve the context from the knowledge base when it needs it. So this is how we can implement a simple RAG in our Flink job. In the next slide, so we have solved the challenges now. In the next slide, I would just like to walk you through a demo of a proof of concept of what it looked like. Before we play the video, because this video is quite fast, there's a lot going on. So I just want to give you a heads up on what you are seeing here. So on the left-hand side, this is the simulation of the field of the game itself. And on the right side is So on the right side, you will see two terminals. The top terminals, the top terminal is the commentary generated by the fast commentator or the fast path. And the bottom terminal is the slow path or the slow commentator. Okay? Yep. So I would like you to focus your attention on the left-hand side, on the field itself. So currently we have two teams that are playing against each other. There are two players each. Blue team has Alice and Bob. And on the red team, there's Carol and David. All right, so I hope you enjoy the demo. And what you're seeing here is the blue team and red team facing off each other. It started from the blue team making an attack, and that the ball was intercepted by the red team, and the red team managed to counter-attack successfully. And also hope you get to see the filtering in place as well. Not every frame was generating a comment or was sending a prompt to the LLM. Only those where there's something exciting or significant going on would warrant a call, a prompt to the LLM. So next, I would like to show you a few screenshots from the demo just to highlight what was going on. So the first thing is when the ball was first intercepted from the blue by the red team. So here we can see that the fast commentator actually made a mistake here. It thought that it was a pass, but actually it wasn't. The ball was intercepted by the opponent. And the slow commentator got it right in this case. So the slow commentator here questioned whether Alice from the blue team has misplaced her pass to someone from the red team. And if we look at the explanation that was given or the chain of thought behind it, here it correctly identified that the ball has moved from Alice's position to a new position. And this new position matches David's coordinates position, suggesting an interception by David, the opponent. The next event that is worth noting is the ball passes. So if we go back to the previous slide, yep, thanks. When the ball was passed between the red players, the fast commentator here correctly identified that the red team is counter-attacking, and the slow commentator gave out an even more detailed commentary saying that David finds Carol with a nice pass. And if we look at the chain of thought, again, the ball has moved from David's position to Carol's position, which indicate a pass between the red teammates. So it's great that it was able to identify these two types of event that was happening. And the next thing that's worth noting in the next slide is spatial awareness. So the LLM in this case actually was able to make sense of this X and Y coordinate quite well. For example, when Carol and Alice were quite close to each other, all the red and the blue dots, here it actually correctly identified that Carol is marking Alice very closely, or Carol is defending against Alice very closely, and the fast commentator was able to pick up on it. The second thing that shows spatial awareness is when the team scored a goal. So in the chain of thought, it correctly identified that the ball has reached the coordinates of the blue team's goal at this coordinate. This means a goal has been scored. So again, making sense of this coordinate is something that the LLM did quite well here, which I think makes it suitable for this use case. And another thing to note is that the fast commentator for the goal scene, the fast commentator was just a tad bit faster than the slow commentator in saying goal. And I think it is in key moments or climactic moment like this where the fast commentator adds a lot of value, because in this kind of very exciting moment, right, you almost want to give an instant reaction to it. So I think the fast commentator definitely helped in reducing the latency here to ensure a good user experience. So this is a demo. I hope you enjoyed it. And next, before I end, I just want to talk to you what are some potential future big ideas for this. The first thing is cross-game commentary. So we could even have commentaries from various ongoing games being joined or coordinated or orchestrated by a Flink job. And that helps, right? Imagine if you are watching a game like Olympics, for example, where there's a lot of different sports that's happening at the same time. If you can kind of cross-pollinate or cross-join this kind of commentary, it just makes the whole user experience a lot more enjoyable. The second ideas I can think of is personalized commentary. Now that we are not relying on a single human being to generate the comments for us, but an AI model, we can actually let Flink to enrich the prompts with user preferences or any user reaction as well. That way we can tailor the commentary to be even more personalized, even more enjoyable. The third big idea that I think is quite exciting is interactive commentary. So imagine if the user can also provide feedback or questions as another source to the Flink job to start kind of a conversation with the AI commentator. That would make the whole experience quite enjoyable as well. So these are future big ideas that I look forward to, and that is made possible with Gen AI and Flink for real-time as well. So this is my talk on real-time generative AI with Flink. I hope you enjoyed it, and thank you all for coming. And I just want to give a special shout out as well to friends and colleagues as well for their inputs to make this talk possible. Thank you, everyone.